Good afternoon, everyone. Welcome to Parsons Technical Webinar Series. I'm your host, Jessica Bennett. Today we have Jim Schutz with us, presenting on the unraveling complexity through fate and transport numerical simulations in a tidally influenced density-driven flow regime, which will make a lot more sense once we get in the technical portion of the presentation. Next slide, please. So just a few housekeeping items up front. We'll keep all phone lines muted during the presentation to keep background noise down, and we'll be able to unmute yourself during the Q&A session at the end. If you have any questions throughout the presentation, you can enter them into the chat at any time, or you can raise your hand at the end when we get to the Q&A and ask your question live. This webinar has been approved for 1 PDH credit. If you'd like to get a certificate for that PDH, there is a link to the attendance form that will be posted in the chat a couple times throughout the webinar. You can go to that link, download the form, and complete it. There are 4 multiple choice questions in that PDH attendance form that you would need to answer. And those questions will be posted in the chat also in a moment, just so you can kind of see what those are and be looking for that content. If you have any issues downloading the form or can't see the chat, you can reach out to us and request that form to Daniela Savin at parsons.com. And finally, this webinar is being recorded and will be posted on the Parsons YouTube channel in the next week or so. Next slide, please. So a brief agenda, I'll introduce our guest speaker, Jim Schutz. He'll give a core value moment to start off with before getting into the technical presentation, and then we'll wrap up at the end with a Q&A session. So Jim is a principal hydrogeologist and technical director of environmental geological services with over 24 years experience, 21 of which have been at Parsons. He specializes in groundwater modeling, advanced 4D visualization modeling, and investigation and remediation of sites in complicated geological environments. His early career consisted of surfactant remediation research for coordinated solvents, as well as development of virtual reality educational platforms. And he also worked as a gold exploration geologist in Eritrea and Greenland. He earned his BS and MS in geology at the University of Buffalo, and he is a professional geologist in New York and Pennsylvania. And with that, I'll turn it over to Jim for the core value moment. And Jim, I think you're still on mute, maybe?
All right, thanks for the introduction, and thank you all for joining today. I think this is a very exciting topic, and I'm happy to present it to you. Hopefully you enjoyed the presentation, and feel free to follow up with any questions that you may have. For the core value moment, I'd like to talk about integrity. So when we think about integrity, I think it's kind of a broad topic. So I found myself asking, well, what is the actual definition of integrity? The definition is the quality of being honest and having strong moral principles, moral uprightness. So strong moral principles and moral uprightness. So what is moral then? So moral, the definition of that is concerned with the principle of right and wrong behavior and the goodness or badness of human character. And I think that's what integrity really comes down to, is our personal human character and how we behave in terms of being right or wrong. And really, I think it boils down to a lot of truthfulness. In engineering and science, integrity plays a profound role. We do have our checks and balances and our peer reviews, but honesty and truthfulness are fundamental requirements at really all levels. And this includes truthfulness to yourself or to oneself. What I like about particularly my team at Parsons, we have a collective group integrity. Since it is a core value moment, we have discussions about integrity, and including this one here. And through the collective group, we can support each other. We have a team, we work as a team, and at the same time, we think critically about our projects and our processes, and all that leads to the very highest level of integrity. So acknowledgements. I'd like to first acknowledge Robert Stutzley from Dow and Rick Wenzel, former project manager from Dow, who were both instrumental in this project going forward, as well as the Parsons project manager, Jack Button, and Parsons project manager, Parsons professional geologist, Jeff Snell. So the agenda here, I'm going to go through kind of a theme a little bit about numeric modeling and some sort of bigger picture reflections and some of the things that I've learned over time and how I've evolved as a numeric modeler. Going to go through the groundwater modeling process, talk about numeric modeling really as a sort of a direct educational piece before we get into the site example, try and give some definitions and some understandings of numeric modeling, what it means, what are some of the limitations or adaptations of it, how is it derived, all background stuff to try and make you all, either as project managers, as hydrogeologists, or as groundwater modelers or future groundwater modelers, a little bit aware of some of the terminology and the processes that are the backdrop to groundwater, to numeric groundwater modeling. And then we'll get into this site example and go through site setting, geological, hydrogeological environments, the groundwater model workflow, the calibration, and the results. So for theme here, I thought a lot about this slide. And my position has kind of changed over time, and this presentation is related to that. For the sort of advanced numeric modeling, there's often barriers to entry in order to like pick that skill up and really become proficient and very good at it. And so I've thought a lot about those barriers to entry and what they mean, why they're there, how they were somewhat institutionalized in the early years of ModFlow. And my position over time has been to try and remove those barriers to entry. And in short, in part, this presentation is related to kind of opening up the world of numeric modeling to others. So some of the barriers to entry that exist for one reason or another, there's really an esoteric culture. And by that, it's kind of a take from esoteric religion where you can only learn something by being directly taught it and mentored. Numeric modeling and the numeric modeling community suffers a little bit from that. There's a reason for it, and in some ways it's good, but in other ways, this esoteric culture prevents others from sort of picking it up, learning it on their own, or figuring out the discipline itself. When ModFlow was in fact first developed, it was developed to be complicated. The early designers wanted to make it less accessible because they were concerned about it being abused or corrupted. And frankly, I think over time things have changed and there's improvements to that. But obviously, if we're going to talk about inclusivity, then we don't want to develop things purposefully to be complicated such that it's exclusionary. And it's a complicated process in its nature. So not only is it complicated a bit by design, but numerical math is no easy thing to pick up and learn. So in groundwater modeling tools, it's a very intense software with lots of options and not a lot of direct guidance at times for site specifics. So that's just another barrier to entry, which I think can be overcome. And then we have the lexicon, which I think is something that every discipline has, whether it be statistics or engineering or plumbing. Every discipline has a lexicon, and you got to learn the language a little bit. The numeric modeling has a lot of them, such as numerically intractable. And some of these, they sound overly complicated, but they're really not. It's numerically intractable essentially means, oh, the math, it didn't work. Okay, why don't we just say that instead of numerically intractable? Parameterization, really the objective of defining and assigning and finding your best parameters. Heuristic. Heuristic is really another word for rule of thumb, or in some cases, trial and error. So, it sounds much more complicated than it is at times. And this one I love, ill-posed problem. So an ill-posed problem is the opposite of a well-posed problem. Again, lexicon, sometimes complications that we don't necessarily need. It's really a mathematical definition that goes back to Jacques Audemars. I believe he's a French mathematician in the 1800s, and he developed this concept of a well-posed problem. So a well-posed problem is one where it has three criteria. First criteria, a solution exists. Second criteria, that solution is unique. Third criteria, that solution is stable. And by stable, it means the solution's behavior changes continuously with the initial conditions. So if you change initial conditions, the solution changes accordingly. Now, an ill-posed problem is one that does not meet those criteria. So, for example, a solution may not exist. In other words, it may be numerically intractable, but math doesn't work. Number two, there may be many, many solutions that are just as accurate as the one that you found. So the solution is not unique. And third, it may be unstable, meaning you may change a parameter and it starts and the solution changes in a certain way, and then you continue to change that parameter and the solution takes a different course. So this ill-posed problem, I think, is just fascinating, and I think it's why numeric modelers are who they are, because if you were asked to solve a problem that may not have a solution, if it does, it has many solutions, and you're not really going to have a fun time trying to predict that solution. That's something that I sign up for because it just sounds awesome. I like the challenge. So I guess in short, part of this presentation, as I mentioned earlier, is one of my current missions in life in terms of removing barriers to entry for a more inclusive and diverse community of groundwater modelers. All right, so let's go through the groundwater modeling process. This is back from early ModFlow manual, and each one of these all have pretty significant importance depending on your model and your site. So define the purpose, build your conceptual model, build your mathematical model, which is essentially this box here, figure out what your code is, run the, develop the code. Is the code verified? No. If the answer is no to that, if you cannot verify your code, which is a very specific process, then you go back to reprogramming it. A lot of times you'll tie in the analytical solution. So the analytical solution is the comparison such that your numerical solution is verified. And once you hit yes, then you go on to model design, add in your field data. The section here, comparison with field data. We have calibration, including sensitivity results, and then we have verification, which seem very similar, but are separate processes. And then we work through prediction. You notice the asterisks here. Your prediction should also include your sensitivity analysis. So you don't normally get a single answer. You might get a range of answers based on your sensitivities. Presentation and results, and then post-audit. Sometimes if you have the ability, you collect more field data and check your model with a post-audit, and hopefully not all the way back to the conceptual model, but at times you revisit this as you build your model up with additional data over time. And we'll talk a lot about that buildup of model over time because the case study really represents that. Analytical versus numerical. So we talk about math and two forms that are analytical versus numerical. And you may hear those phrases sort of passed around. Sometimes they're used in substitution, which is incorrect. An analytical solution is a direct solution like this function on the left, very simple function, x minus 15. How do we solve that? We add both sides by 15 and then x equals 15. It's very simple, in this context. And it's theoretically based, it's an exact solution. but it can be time consuming for multivariate equations, particularly partial differential equations, which is the which is the flow model for groundwater flow. You end up with high computational times and almost the impossibility of solving that over time. And so early mathematicians realized this. They realized that there are ill-posed problems, and numerical solutions were developed in relation to those ill-posed problems. Here's the partial differential equation, the PDE for groundwater flow. It's hard to solve analytically, so numerically you can solve it, but it comes with certain caveats. And here you can see, it's somewhat readable. You have your hydraulic conductivity field, X, Y, and Z, your sources and sinks, and then your storage coefficient, and then head and time. So with numerical math, and I'll talk about it in context of the finite difference method because that is what's mostly used within ModFlow. The idea becomes, okay, we're not going to solve this analytically. Let's solve it by approximation. And it in the process iterates. So we try x equals 1, and we try x equals 40, and we compare the difference and try again. And this attenuating sine wave here represents that the reduction in the reduction in the iterations and in the error until you reach your error to be less than what you assign as your convergence criteria. That's when your model is essentially converged because you've reduced the difference between the two answers to an acceptable level. And what you notice down here is we take this PDE and we then transform it into a much simpler equation. It may not look simpler, but it really is because you've removed all the derivatives. So now we just have conductance on one cell side, conductance on another, and another, and another. And it's really just a matter of conductance and volumetric flows and specific storage, head, and time. And these are now deltas. So it's essentially transposed this PDE into a more easily solvable solution. I'll refer to the cell structure a little bit here and there during this presentation. So this is a depiction of what's happening in this equation where you have a cell, i.e. a cube in this case, in the center of 6 other cubes. So every side of the cube has a face. That face represents flow, represents an area where flow can happen. So what ModFlow is doing, or any numeric finite difference method in this case, would be transferring water from cell to cell. And that transfer of water is restricted to the conductance and based on the hydraulic head differences. And then in some cases, you're adding water in directly through sources and sinks, and you have a storage factor. So a little bit more on numerical methods. It approaches complicated parameterization with an iterative convergence approximation. So yeah, again, lexicon, that sounds overly complicated. What I've tried to describe in the past few slides is that it assigns parameters with an iterative convergence approximation through this iterative convergence approximation. It's typically a user-defined convergence criteria. So you want your model to be as accurate as possible, so you reduce your convergence criteria. And a lot of times you would set the convergence criteria like 100th or 1,000th less than what your measurable accuracy is. So if you're measuring hydraulic heads in the field and that's your accuracy is 0.01 with a water level indicator, then you would set maybe your convergence criteria to 1/10 of that or 100th of that. It's an approximation and it's non-unique, but that doesn't mean it's unusable. As long as your approximation is as precise as you need it, and you can overcome some of the non-unique factors, then it's a perfectly valid tool, and obviously it's used all the time. As discretization becomes more fine, all numerical methods become unstable. That's from Habre 2013. And what happens sometimes when you build complicated models is you cannot reach convergence because the error does not attenuate, like I showed in the previous slide, to below the convergence criteria. It sometimes just starts bouncing all over the place, meaning it doesn't, the error doesn't reduce over time, and you just end up in a loop, and then you fail to converge, which is numerically intractable. Example for mod flow, it's a finite difference approximation, and then the main releases of mod flow began in 1998, update in 1996, 2005 came around and lasted for a while, and it is still around. I think it was updated in 2017, if not before that. And then USG and ModFlow 6. And USG and ModFlow 6, those really were a significant change in the structure of how you can discretize space, which really became a good advancement in how we build models. So a little bit more in ModFlow and how it was built, and to some degree why it's called ModFlow. So here we have our PDE for groundwater flow. This depiction here is back from 1983 when they were developing ModFlow. And the concept here, this inner box, is the idea of a 1970s or 80s stereo system with a receiver. You had a receiver in the middle, and you would plug in, let's say, your record player or your CD player, or your 8-track player, your synthesizer. All those get plugged in, or all your components basically get plugged in to the back of this box. So they took that concept and they said, okay, we have certain things that we have already solved and are ready to plug into the groundwater flow equation and provide a solution. So if you wanted wells, you use the well package. If you want rivers, you use the river package. If you want drains, you use the drain package. If you want a simple implicit procedure, you plug that into the side. And these blank areas, they really allocated space to say, okay, we're going to adapt this over time. And in order to do so, let's keep some slots open so that we can add in additional modules. So the mod of ModFlow is for different modules. Here we have an example of the grid structure. So there are layers and there are rows and columns. And for each cell, you can you assign a set of parameters for each cell. Just quickly about ModFlow, it's not really a black box. Some software packages are easier to understand than others in terms of the front interface, the GUI. But ModFlow is really a set of files, a set of text files written in Fortran, and it's a pretty readable set of files. In fact, when I'm training people, first thing I do is walk through each of the text files and show them what the important parts of it are. So some recent updates with ModFlow, USG, and ModFlow 6, which are numerically fascinating. The grid structure on the left here, which is ModFlow USG, that stands for unstructured grids. If you remember in the slide I showed earlier with one cell and then 6 cells around it on either face, you always had to have one cell connected to 6 cells, one for every face of that cell. What we have here is one cell, and just on the side, we're looking top down, it's connected to 3 cells on the right-hand side. So now you can go from one cell to smaller cells and essentially construct what is considered a nested grid. So you can have a grid within inside a grid, which was a real game changer for the way we build models and the way we can increase complexity in the area that we need to without water balance issues because of oddly shaped rectangular cells, or without having significantly long run times. So in numeric modeling, you're always balancing your complexity with your runtime and your computational efficiency. You don't want to build something that takes more longer to run than you actually need it to. So a little note here, nested and quad tree grids. There's also all these other types of grids that are now sort of allowed. We really in the industry, mostly I'm seeing nested and quad tree grids. You might see some of these other triangulated grids or sometimes Veroni polygons, but those are kind of rare. In a quad tree grid, you can see here where it's, it telescopes into the cells. And the addition of connected linear networks was a real game changer, which applies an analytical solution to pass water around for, let's say, a pumping well, or if you want to take water from an extraction well and then put it into an injectant well, you can do that through CLN. So model calibration, this is also this is one of the important parts of numeric modeling. This is where the inversion lies, meaning groundwater modeling. It's not a forward model where you just put parameters in and push go. You put your parameters in, you push go, you compare it to reality, and then you change your parameters. So you're inversely assigning your parameter values based on your observations in reality. It's a comparison of historical data to simulated results. It involves systematic error reduction through parameter change value iterations. So we're changing our parameter values iteratively and then trying to reduce the difference between the simulated and the observed. So we have a target hydraulic head. We run our model, we try to hit all our targets statistically the best as possible. That statistic is called the objective function. We want to reduce the objective function to the extent practical. And when you see these plots, this observed versus simulated, your one-to-one line here gives you a graphical reference to look for where your data are spread. And a lot can be understood from looking at these types of graphs. There are various error reduction criteria. Most of the time we look for sum of squared of residuals, and then you try to reduce that as low as you can within your specific model. There's really no universal criteria for when a model is considered calibrated. It's a non-unique solution. So what does that mean? That means there are many other solutions that exist which are just as accurate and just as acceptable. Lawyers don't like to hear that, but it's true. And a simple version of this, and I'll try to explain it in two different slides. So here you have your objective function, which is essentially your error. Here you have your y-axis, which is a variable, a parameter, and your, let's just call them variables x and variable y. So, this global minimum, the bottom of this three-dimensional parabolic shape is the lowest you can get in your objective function. So that's the global minimum. That's as good as you can get for your calibration. What models really look like is many different local minimums and one global minimum. So the idea and the analogy goes is you put a ball in a corner somewhere, and then it slowly rolls down and ends up in the bottom, which is your best calibrated model. What happens over here is you put a ball in and it rolls down and hits a local minimum, and you think, aha, I have the best calibration that I can ever achieve, but it's not necessarily the global minimum, and there are many other local minimums that exist. This is a simple, two variables and one objective function. So in real numeric modeling, there might be hundreds or thousands of variables. So many, many, many local minimums. But that's okay. There are tools that we have to understand if the local minimums, how much they change, and you essentially, through sensitivity analysis, you can develop a suite of just as accurate models to compare. Looking at that a little bit just different graphics, really. Here you see the local minimum and the global minimum. And you can see if you got sort of stuck in this local minimum, you wouldn't know that there's a global minimum over here. There are newer tools that have come out to try and, cross this saddle here. So if this ball was rolling down, originally it would have ended up in a local minimum over here. There are ways and mathematical techniques that are kind of out there and growing and in use to reach over and find your global minimum. We can't really talk about ModFlow without talking about PEST. PEST was paramount in automating calibration. There are other auto calibration tools out there in the past, but really PEST has become, essentially one of the most used automated calibration tools. So it automates calibration. It has ingrained in it calibration constrained uncertainty analyses so that you can better develop your uncertainty, and that runs the model many, many, many times so that you can help find the best optimal solution. And over time, we have the ability for more probabilistic models and stochastic continuum models. So with PEST, eventually came along the use of pilot points, which you put in all these pilot points basically, and you can develop your hydraulic conductivity field, not as a bunch of zones that you've assigned, but as a continuum based on probabilities. And in that regard, parsimony is less considered, meaning you can build very, very complicated models. They have very, very long run times. So whether or not you want to do that or not is, based on your project and your objectives and your budget, but it is less considered. Considerable enhancements over the past decade. Past, if you used that 20 years ago, you made it maybe, we're running into failures and errors and whatnot. It's become a lot more usable. It's tied in Monte Carlo statistics to help with finding and developing all your a suite of analyses. And more recently, this IES has become fairly popular, which is an iterative ensemble smoother, which helps to look for a suite of, an ensemble of outputs for you to develop a range of estimates and predictions. So on to the case study. So why is this project relevant? What it means to you? It's a complicated project, has complicated geology, hydrogeology, and anthropogenic environments. It involves what I term this technological advancement cycling. So that's what I have depicted over here. And we see this, I think, across all technologies. You have an aspiration for better problem solving and removing your assumptions. You write all these assumptions and then you get questioned on them, and you wish, that you could have just not had to make those assumptions. You have this quest for advancement. You make the advancement, you implement the advancement, and almost instantly you're like, oh, well, how can we advance further? And so that's where advancement begets advancement. Demonstration of continual improvement in the CSM, increasing resolution and studies. So over time, this project evolved, and as we needed to find more answers, we sought out to answer questions. It represents a site where complexity can be resolved, and you can find the most appropriate and simplistic solution, even in a complicated setting. Moreover, this project had a drive to move from decades of pump and treat to a more sustainable remediation, and the three-dimensional groundwater model that we developed really was a useful tool in that process. So it's a multi-layered system, and on the right-hand side, this is a CPT log. So where you see yellow, that represents sand, where you see red, that represents clay, and these were, pushed into the subsurface. And I'll get to a geological cross-section in a second, but we have sand 1, sand 2, and then sand 3. And a couple of things to notice, which were critical to understanding the plume dynamics and the plume pathways, is you notice clay 2 pinches out, And then we have this gap where sand 2 is in direct hydraulic communication with sand 3, and there are downward gradients. You also notice some of the transitional zones. Those are inner beds, and those inner beds, you have a clay and then a sand, then a clay and a sand. Those really were a source of mass, so those became important to the project. There were gradational transitions. So you notice on this CPT log, as the slope goes to the right, this this right kick, which is of shallower slope than the kick back, that that represents a gradational change in grain size. So even within the sand, this is normal bedding, so it's increasing in grain size towards the bottom, so increasing hydraulic conductivity. It's a tidally influenced setting. There's density-driven flow, and we have static and pumping head data. So just an example here, again, normal bedding. This is not from the site, but it shows you what reality actually looks like. Finer grain sands, grade 2 cobbles and gravel at the bottom, and then a hard change to the silt and clay. Tidally influenced, so just to the south of this image here, the white line represents the model domain. The inner smaller rectangle represents the site itself. To the south is the Gulf of Mexico, and because of that, the salt water exists in the river itself, and that has produced density-driven flow, and it's tidally influenced. So again, there's a desire to move out of pump and treat. We did additional characterizations. All of those you can see here. And then we developed a three-dimensional model with CWAT. And we really applied the principle of parsimony to the site conceptual model. I'm not expecting you to read those. So this is what it really looks like. Sand, alluvial aquifer, semi-confining, upper citronelle, semi-confining, lower citronelle. That in cross-sectional view, we have the alluvial aquifer, the upper citronelle, and the lower citronelle. And here you can see that pinch out of the clay unit, which allowed concentrations to drop into the lower citronelle. We're going to focus a lot on this plume down here, and I'll show that in the next couple of slides. So this is a plume that is diving. So we have high concentrations in the alluvial aquifer. That's sand 1 at the top. Concentrations are greater than 1,000 micrograms per liter. And some of the plume has been depicted as migrating towards the river. However, much of the plume apparently has migrated downward into the upper citronelle. So the green is that middle aquifer, upper citronelle, and you can see that there's overlap between the alluvial aquifer and the upper citronelle. Plume has migrated down, and actually it's migrated to the northwest in the upper citronelle. Remember when this site was first developed, everyone assumed that, as I would have too, and I wasn't involved in the early site characterization, but when I got onto the project, it seemed very logical, and I made the assumption groundwater should be flowing to the river. And so anyways, the upper citronelle, you can see it here in green, that then drops down into the lower citronelle up to the northwest. And you can see the overlap here where the plume drops down into the lower citronelle and then sort of migrates off to the northeast in sort of a thin shaped plume. So what that looks like on cross section, here we have the plume on the, if the source area is basically in here, and then to the northwest, you have the plume, but we'll focus on the northeast. Plume migrates down into the upper citronelle, then down into the lower citronelle, and then farther out to the northeast. So the workflow here for the model development itself, we take all of the physical parameters, regional information, river head and salinity, hydrogeological testing, boring log, CPT. We fold that all into the model structure and the solver. And then, we select mod flow for initial runs and testing. So we had multiple calibrations in this process. So the green shapes represent different calibrations. So even before we built in the density, which adds, a significant computational time, we calibrated to static heads from 2018. Then we further developed that non-density model with manual calibration. We come down into initial density-driven model. We run PEST with calibration and sensitivity testing. We tie in river concentrations in order to develop a density-driven flow model with the CWAT version 4. We loop our way over and we write our first phase technical memorandum. So the regulator in this process, this is a requisite. The regulator was highly critical of the project. We were developing the CMS, the corrective measure studies, and we're trying to work our way through those negotiations. I didn't want to produce a model that was overly complicated and spend our clients' money and time to only have that be sort of rejected by the regulator. So we did this in phases. Phase 1, we presented to the regulator, who was a mathematical model at some point, and we said, all right, what do you think of this? And we're able to work through any comments and questions that they had, and then move on to additional calibrations. So then we completed the pumping model calibration, active pumping and steady state and active pumping heads. We completed some particle track corrections, and then we folded in one-dimensional fate and transport of one compound to represent really it was the most non-reactive and recalcitrant compound at the site. So it really represented a conservative view of the plume, and all other parameters sort of would fall within that same plume fate and transport envelope. And we looked towards some field verification by collecting additional data, and then wrote phase 2 technical memorandum. So this slide really goes through the stress periods. The first model for CWAT was long-term natural conditions. So you got to run CWAT a very long time in order to have the release of the saltwater component build up and develop a density wedge. So that ran for 500 years and became a calibration point. And then we had site historical operations. So 42 years of operations, including chemical release at the beginning, year 0. And these were similar to non-pumping conditions because it was before the pump and treat came on board. So it was really similar to step 1, developing the density-driven wedge. Step 2 was develop the plume before initiation of pump and treat. So then we initiate pump and treat. We do that for 12 years. We're pumping from 3 aquifers, recovery of the plume, and that becomes a calibration point. This is an overly simplistic example of calibration, and I like this because it is an understandable communication tool to non-modelers, and it represents the calibration process such that it sort of resonates. And when you can communicate, when you can resonate with people, I believe they're more likely to understand the process and more likely to respond favorably to your predictions based on your model. So the green is the absolute residual mean, sum of squares, and blue you can see through just a handful of runs. There are thousands of other runs in the backdrop here, but some trial and error calibration. And Then we start running pest, we get improvements there, and then we really reach our target, and we drop below our target. Some of the squares actually back before we started running pest, but we were able to drop it much more significantly. So our posterior model runs here are much improved compared to even our prior manuals. Here is the plot, the one-to-one plot. So simulated on the left, observed on the right. And you can see it's broken out into different aquifers, but amongst all of the aquifers, we get a good calibration. So these are some of the results. And the color scale is the lower citronelle, so that's the deepest aquifer, salt concentration. You can see the highest concentrations are this yellow and orange area. So we have the highest salt concentrations in the lower citronelle, really in and around this area. But generally speaking, the concentrations grade from highest along the river, as you would expect, up to the northern part of the site. This is essentially part of the saltwater wedge. The particle paths here, so these particles are starting out in the alluvial aquifer, and they curve down this way. They're actually going down. We're looking at the particles through all the layers. So three-dimensionally, we're seeing these particles drop down into the lower citronelle. And then when they hit the lower citronelle, they actually migrate away from the river because they're now down in the saltwater wedge, and that density-driven flow is pushing the particles out. And then there's a natural gradient off to the east. And so this is 500 years of saltwater development with CWAT and non-pumping for 42 years. These are the recovery wells, but those are not operating during this model scenario. So again, you see the particles drop, migrate off to the east. After 12 years of pumping, those particles migrate out and then are partially being recovered by the recovery wells. And you can see the saltwater wedge has now been retracted slightly towards the pumping wells. This is just a quick video of what it looks like in 3 dimensions. You're kind of looking somewhat down and into the plume from the south side of the river. You can see the particles, they drop down very quickly. That's a function of the scale and the x-axis being distorted to the y-axis just for graphical purposes. And then you can see the particles track off to the east. You can also notice some of the particles start to divert right about here and divert down to the recovery wells. So again, contaminants dropping down into the lower citronelle and then migrating quickly off to the east, and then some of them being recovered. However, some have really left the barn, as they say. Now, if we look at 1,4-dioxane and 42 years of plume development, here we have particle paths with the pink shading representing the 1,4-dioxane plume. This is before pump and treat. Pump and treat is enacted and starts to morph the plume and really almost drop the middle of the plume to very low concentrations. Meanwhile, there's still the plume head out here, which is not being captured by the pumping system. And then if we compare to concentrations, so this is the model in the orange square, slightly translated to the plume centerline, and the 2017 groundwater result from analytical data. So these are, the gray are the empirical data, the wells sampled in 2017, and then the orange is the model result, which is fairly, I would say, fairly good calibration for a faint transport model, because they can be quite tricky when you're trying to track the plume centerline. This whole project really allowed for evolution of the groundwater model. It was built up even before the project that I'm showing now was started out as a very simplistic one-dimensional flow model, and then evolved as the project needed it, as we wanted to answer more questions. We built the model complexity up over time, and we're able to have more detailed geological structures. Represents fate and transport in complex flow regimes, and advanced through processes and site analyses. So in conclusion, increased complexity is sometimes required. High resolution sampling can support groundwater modeling, and decisions can be supported with site-specific detailed numeric modeling. And that is the rest. That's the end of the presentation. Does anyone have any questions?
Thank you, Jim. That was a really informative presentation on some of the fundamentals of modeling, but also how numerical modeling can be used to improve the CSM and ultimately remediation of some sites with really complex hydrogeology. So I know I found that really interesting. If there are any questions, you can either raise your hand and we'll call on you. You can ask your question live, or you can enter your question into the chat and we'll read it out for you. The link to the PH form has been posted, so if you had any issues, let us know and we can get that to you if you want to get a PDH credit. So I see the first question we have is from Jordan Collier. Do we parsons shoot the logs ourselves?
So, Jordan, I want to understand the question. By what do you mean by shoot and the logs? Are you talking about the CPT logs? Like, did we install them ourselves? And for the CPT logs, we did not. We had a subcontractor that did the CPT logs. Yeah. So I see your secondary question there. Thank you, Jordan. Yeah, we hired a firm. I can't think of the firm, but they did the CPT logs. They provided the data in usable formats. They had a nice output, and then we were able to use that and work with the rest of the project team. And I'll just go through the questions here myself. Why did you use CWAT and not USG or ModFlow 6? So this project was began in its early conception before USG was really popular. It was even before ModPath was folded into USG. So I could have converted it in the later years of the model, but I'm generally software agnostic and hardware agnostic. I don't put a lot of emphasis on updating, code unless I need to. My objective is to provide our customers with the best solution in a cost-effective manner. And if I have a solution that's working and is computationally correct and providing good results without with expected runtimes, then I don't necessarily update the code. And this is a case of that. I think in some of the later runs, I started maybe looking at USG, but yeah, it's a good question. Generally speaking, I use a code that is appropriate for the project. And if I'm getting to the end of the project, I don't necessarily upgrade the code. What approaches to use in managing models with long runtimes? So there's ways to reduce those runtimes. There's little tricks and tools. There's even software packages and within particularly Pest and Pest++ that help with reducing long runtimes. But it becomes a change in mind as a modeler in a way that you just have expectations of the number of runs you can actually have. So if you're running something like Pest and you have long run times, then I'm not probably going to run a model that takes 30 days to solve. I've convinced myself that that's probably too complicated for most of our projects. So really, I have an expectation in the number of runtimes and I adapt accordingly. And then I guess the last way to handle long runtimes is more reliance on algorithms. so you have less time to really sort of go back and see how the model's responding, and you really have an expectation that, okay, this is going to be the output that I'll have to go with. Has the model been calibrated to steady state or both? For flow or only flow, both transport? So this model was calibrated to 3 steady state solutions, or 3 steady state time periods. It was a transient model because it needed to be, but the calibration points were very specific points in time. And it was calibrated to head. And, I guess in the last slide, I was really showing more of a verification and not necessarily a calibration. How is the simulation of complex geological features like angled faults and steep hydraulic gradient incorporated into mod flow models? Great question. With the inclusion now of unstructured grids, we're able to better explicitly involve angled faults and steep hydraulic gradients. So we're actually able to build that into the structure itself with the unstructured grids. There's ways to do it implicitly, meaning you assign your hydraulic conductivity fields to help with, describing angled faults and steep and steep structure within an unstructured grid, but within a structured grid, you can do it implicitly, but the structured grid has some limitations, and therefore, like I said earlier, the unstructured grid really helps with that. And furthermore, the CLN package that actually gives an analytical tool to help with these angled faults. So thank you for the question. Aside from being a better understanding of plume travel, how did the modeling improve the project? So not only did it improve, really just our understanding of the plume and our understanding of how the plume got there, why it got there, this project was part of a bigger phase in our RECRA regulatory environment, where we're trying to finish the CMS, the corrective measures study, to find what the best remedy would be. Again, get out of pump and treat. How are we going to develop the best future remedial action? And this model itself and the buildup over time and working with the regulators, I believe really helped with approval of the CMS, because it gave the regulators confidence that we knew why the plume got where it was, and we're able to demonstrate that, and then we're able to use it as a tool to evaluate the site. And so I think the short answer is approval of the CMS was supported by this mathematical modeling.
Maybe we can go to the next slide. If there's any more questions, there's still like a minute or 2 left. But in the meantime, next month's webinar will be on May 10th, and it will be presented by Les Cordone on lessons learned in applying PFAS absorption technologies to surface water and groundwater. So we hope you can join us for that. I see there's one more question that came in.
Yeah, I'm trying to research what Occam's razor is. I don't know that one, Joe.
Oh, that's this Joe from BG Occam's razor is the whole thing. Keep it simple.
Yeah, more or less. Yeah. The principle of parsimony is, keep it simple, build complexity as needed.
Thanks.
Yeah, again, it's just a more fancy way of saying the same thing, which people like to do.
Okay,
hey,
well,
Jim.
Sorry, go ahead.
Oh, sorry, hey, Jim, this is Lucy from Kirby office. I basically have a question. I just want to check with you, like, how many computer resources you used for this specific project? Like during the calibration, I imagine if it takes a long time, it's gonna need a lot of effort there, right?
Yeah, so I had a dedicated machine for this. We have you know, beyond our regular assets, within the Parsons assets, we have analysis machines. So it's a higher CPU and higher RAM. I had that basically dedicated so that I could do other things while test was running. And, you know, some of my run times, for example, were 30 hours. I think I got that down to about 28, but, you know, that was really because of CWAT, not because of pest. So yeah, really just one computer, but dedicated to essentially running just this model.
Yeah, because like, so your method by using past is actually run like a one run after one run, right? So is there we said in past, you could actually run like multiple runs at the same time? They
Yeah,
could
you can run.
communicate.
You
Yeah,
can
maybe
run
save
in,
a different time there.
yeah, pest has the capabilities to run as like parallel processing. I did not do it on this one.
Oh, okay. Yep. Yeah, just curious if you know that.
Yeah.
Thank you. Yeah.
Well, thanks for the question.
Okay, with that, I think we will wrap it up for today. Thank you to everybody who joined us for today's webinar, and we really hope to see you again in May. The recording of today's webinar will be up on our YouTube channel in the next week or so. So if you missed anything or just want to refer back, you can look at it there. And if you've got any questions, feel free to reach out to Jim directly.